Also next week, next Monday and Tuesday, so 26th and 28th, we have guest lecturers that will be coming from the Glass Packaging Institute, and they will be talking about shipments and distribution of glass packaging. Many how they are basically shipped to bottlers and stuff like this, so that should be interesting. So we'll have them 2 days next week. I'm not done grading your exam. Hopefully, as soon as I'm done, I'll return them to you. So probably sometime next week, I should be able to return them. If we have guest lecture, that means we may have to do that next Friday. So we'll have time to do this. Okay, so any questions or anything before we start? You should all have a handout. Extra handouts, are they over there? Savannah or Dario, are the handouts are back there? Okay, good. So, so we actually talked a little bit about damp vibration, but we did not cover them properly, and we did not discuss what's happening with dampening for packaging application. So we mentioned that for vibrating object, you can think about guitar string or tuning fork. Actually, they're gonna be at some point they start vibrating. Partially, we're dealing with free vibration. Okay, so that means that some of the energy that was basically applied to the system at some point gets dissipated through friction, heat, okay, etc. Okay, or sometimes mechanical means, but it's what's referred to as damping. So this here, okay, represents okay a viscous damp free vibrating system. Okay, so the difference with this equation, what we had before with for just free vibration, is this guy here. Okay, so in this equation we have that coefficient C again is the damping coefficient of viscous damping. If we were to solve this equation like we have done in the case of free vibration, we will end up with a frequency, okay, for that vibration that is a little bit different than what we have for the natural frequency of a 3D vibrating system. And the difference comes in that second term here under the square root, where the damping is involved. This can be regrouped using the critical coefficient of damping that is defined here. So you can play with that equation to show that this is equal to this, okay? And this will be critical damping factor, the damping factor. And we're going to see what this means a little bit later. So this is free vibration, okay? So that means if you were to set the system into motion, you will have 3 different general cases that can happen, okay? So, and that depends based on this value here. If it's larger than 1, equal to 1, okay, or smaller to 1. So if you do have a value under the square root that is larger to 1, that's what you have expressed as a red line, okay, you have overdamping. And what happened in this case is that there's no vibration, okay, in that solution, and the system tends to go back to equilibrium with a long period of time, okay? Critical damping, this is what happens where you have a system that's going back to its equilibrium state, okay, as fast as possible, okay, without any vibration. And if you were in the case where your system is actually vibrating, in the case where you have underdamping, you're going to have the vibration, okay, that's going to be going up, but you're going to have it with an asymptotic behavior that is typically tied to an exponential function. So this is the case where we are more interested in, okay? So in here, for underdamped system, yes.
Well, okay, so for critical damping, you say that's like a fast, I'll call it like death or whatever. It goes
what?
fast. Like it goes fast to like really zero, right? Critical damping.
Critical damping goes down to equilibrium
Fast.
fast.
Okay.
Without vibration.
What would be your description for over damping?
It just goes back to equilibrium with a longer time.
Okay.
For underdamped system, the difference between the natural frequency we used before, okay, 1 over 2 pi square root of k over m, and the natural frequency associated with dampening, okay, is usually quite small, okay? That means the frequency that you notice in here, there's not a big difference, and if you include that dampening coefficient or if you don't. And it also means that the natural frequency for packaging application usually defines the resonance frequency pretty well, okay? So if you go to the next step, as we've done in the past, okay, we go from free vibrating, where we introduce the natural frequency, and we look at what happens with force frequency. So it's the same equation, but you have a source term on the right-hand side that is actually creating the motion, okay? It's not just set into motion and let to go back to equilibrium, it's actually actively shaken, okay? So if you were to do this solution, okay, and work it out, you can reestablish an expression for the magnification factor, or sometimes called the amplification factor. And in this equation, you'll have the classic natural frequency we talked about, the force frequency, and the dampening that plays a role here. Now, if you look at this equation, and you were to plot it, okay, what you will get, again here, it should be understood that, that the absolute value of the magnification factor here. So what you will have here, okay, is you have the case where we're dealing with no dampening, okay, damping here, so that goes to infinity. But every other cases where you have certain types or certain level of damping, you still have a bump, if you want, very close to that ratio where the force and natural frequency is equal to 1, okay? So that's what we were talking about earlier, is that even though you have some dampening in every type of system, okay, you're still going to be faced, potentially, with vibration damage if you have natural frequency of your system that are close to the force frequency at which you are exposed to, okay? So that's still going to happen. So a few statements about what we just discussed and what are the implications for packaging applications, okay? So resonance again occurs when the force frequency approaches the natural frequency of the system. That's what we notice by this bump close to an x value of 1 here. And again, the important distinction, it's not in orange, but it should be, this is very important, or in this case, the peaks are no longer infinite. Obviously, we're not dealing with something that's going to go to infinity in real world, okay, so it's going to be finite. In packaging, we also tend to use the easily calculated value of the magnification factor we used before to estimate, okay, the vibration motion transfer. So typically, if we use the equation we have used in the past to look at what's going to be the output and what kind of vibration we can get as an output, it's usually a good indication to base some design criteria or to do some preliminary design for our system. So it is understood, obviously, that the magnification factor will be somewhat less. Okay, that's understood because of dampening. And obviously, one thing we want to avoid, that's for sure, okay, is over-packaging. Okay, so if you use that approach that we just discussed here is kind of conservative, okay, if you based only on this, you're probably going to get over-packaged, okay? So that means that you may want to always, and that's something that should always be done, is you want to design a package, okay? Try to design the best as you can, okay? Take into account vibration, shocks, okay? Material available, and all these things, okay? Go in the lab and test it, okay? And if it based on the results you get in the lab, that's where you need to go back, okay? Discuss this, remodify, okay, and retest again. So, vibration sensitivity. When you're going to hear this term, okay, you need to understand that what it is, it's defined as those input vibration frequency that has sufficient amplitude and acceleration, okay, and that occur in the environment that can cause resonance or failure of your product or component within the product. One thing that is very important, I think I'm going to assign this lecture a little bit later to you, but is the fact that if you have issues or damage in distribution, okay, and you're trying to find the cause, is that a drop, okay, is that impact, is that vibration, things like this, remember that if you have issues with vibration, that issue should be almost systematic, okay, because particularly if you're dealing with road transportation and your package go on the road all the time, okay, it will be exposed to vibration. So there's no reason why one box out of I don't know how many, okay, is going to get damaged and none of the others, okay. Obviously, you're going to get variation depending on where you are, or you may get variation depending on where you are on the pallet, okay. You've seen in the lab on Monday, right? The box on top will vibrate differently than the box placed under it, okay? And you may have different failure. You may have some that is due to compression, some may be due to excessive movement, okay? But if it's something due to vibration and road transportation, okay, you should have a lot of it, okay? Unless sometimes it happens over a very long period of time, then you're going to have, again, systematic for long shipments, okay? But it has to be the same thing or very similar, and it has to be encountered continuously. It's not like a drop where it can happen for 2 trips in a row and then no one's going to see that drop again for a long time. Does it make sense? So it's important to understand that vibration are kind of inherent to road transportation, so they should happen on a regular basis. Other type of damage, which can include cosmetic damage to the packaging of the product, scuffing is one, should not be neglected, okay? That is very important. And that is true for the product inside the package, okay? But it's also true for the package itself in some cases. And I think I mentioned that as well. If on your pallet, for example, you have your tertiary packaging or secondary packaging is actually the corrugated box that's going to be displayed in the store. You don't want that box, let's say you have a nice photo print on this, to be all scuffed, okay? Because if you are like me, okay, and you arrive in the store and you have the choice between a beat-up box, okay, and a nice box, you're going to take the nice box. And it does not project well the image of your company as well if your box is all scuffed up, okay? And that's true for, again, the box, but also within for the product inside. So, let's see. Information on the vibration sensitivity used to either properly design a package system that will minimize the product's response output to the input vibration and distribution system, or to redesign the product. So, that means you need to look at this, okay, and see how you can adjust. And again, I think I talk about it a little bit later. Yeah, I talk about it later. You need to always think about these things at different levels, right? You need to think about it at a single box level or the product itself, but also at the pallet level, okay? Because these will be different. So to determine the vibration sensitivity, what you have to do, okay? So one thing you have to do, if you can, and again, this is another thing you have to realize, is that these steps, okay, and all of these guidelines, okay, will be used by all companies in the utopic world, okay? It's not everybody who does that. Some people don't have the resource to do this. Some people don't care about doing this, okay? It's different. But if you can, large company, if you have product that is worth doing this, this is what should be done, okay? So the first step here you should identify the natural frequency of the product as well as the natural frequency of the product cushion system. How would you do that? Yeah, the sine sweep, remember? Okay, so you typically will have to set your product on the vibration table, okay, and you'll have to do it at different levels. So first, if you have a product with many components, obviously if you have, clothing, or it's useless. You don't need to do that, okay? But if you have a product with many moving parts, okay, components, okay, that can move freely, things like this, you should first attach the product on the vibration table. That means you fix it on there so it doesn't move, okay, and you shake it, okay, and then you look at if you get any resonance from any of its components, okay. So that's the first step. And then if you notice that these frequencies where you can have resonance are major and associated with the distribution and transport environment, then you may have to think about doing something about it, okay? So, and that means you may have inserts or something that will prevent those moving parts to move, okay? So that could be one thing. The second thing is to look at the natural frequencies, so then with the product and cushion system, okay? If you're going to put then, to ship the product, you're going to put it in a box and you're going to have a cushion system, then you look at how this thing works together, okay? And what was I going to say? Yeah, and remember that the cushion, okay, is there for drops, right? It's there to protect against impact, not vibration, okay? But as you've seen and as we discussed, because of its nature, because it acts like a spring, okay, it does influence what kind of movement the product is going to see, okay, because of the magnification factor, okay? So look at these two together. Identify the vibration of the distribution environment as well. So this is typically pretty well known, okay? Unless you use something pretty out of the ordinary, you should be able to go to standard procedures and identify what frequency are dominant in air transport, road transportation. You can look at what ASTM is recommending, what IST is recommending, and this should be relatively known. Determine if failure will occur with the product and the product cushion system, or the product cushion system vibrated at the frequency and amplitude encountered in the distribution environment. So you may have some kind of a resonance happening, okay? But if the product doesn't get damaged by this, okay, that's good, okay? It's tough enough, it's going to take it, so you don't have to take additional step to protect against it if you don't get the damage. And you also need to repeat, okay, and look at unitized or palletized product. Unitized, palletized means the same thing as when you regroup many of these products together and you ship them together. And in this case, you need to look at stack vibration, okay? So it might be there if you just stack them or you test on a pallet, it's going to be impossible to identify typically if you have the natural frequency of components into your product, but you can see how the stack behaves, okay? And in a way, that may be the most important test you will do if you ship on pallets, okay? And again, what you will see from here, you can take notes of this, is not only damage caused just to vibration, but it's dynamic compression, okay? If you get box failure, and if you do these things, it might be interesting to play with the relative humidity as well, okay? And see if you were to expose the product, the pallet, to a more humid environment, and then you were to shake it, okay? That will change the stiffness of the board, right? Okay, and they may fail, or they may act totally differently as well. So these are important things to deal with. And that's also important to use the right pallet, right? Because if you use a different pallet, okay, that vibration also is going to be different because the pallet also acts a pretty stiff spring, but if you have something heavy on that pallet, it will behave differently. So this, again, I'm not going to ask you any question on these. These are some dominant frequency ranges, okay, for different mode of heat transfer, and what the maximum G level associated with them is typical. So these are the grams, these are gravitational acceleration, so it's 9.81 meter per second square that you multiply by the fraction in front. So, yeah. So, that's something now we're changing from dampening and vibration sensitivity to what I also showed you on Monday in the lab is random vibration. Okay, so at this point we kind of focus on a nice little sine wave. Okay, and we looked at one vibration, one very unique vibration, and what the output will be. But in reality, vibrational forces, okay, experienced by product are due to not only a single frequency. Okay, they're due to many of them. Okay. So, a random vibration is a vibration where the instantaneous value, okay, of acceleration and therefore amplitude is not necessarily available information, okay? So it's a mixture of a bunch of these sine waves all put together, okay? And that means typically statistical distribution are used to be able to reproduce those vibrations or analyze them, okay? This is what is mentioned at the bottom. So this is just a simplest example I can show you, okay? So I just put two sine function, actually, two sine function. So they have different amplitude, different frequency, right? The amplitude is quite different, and you see the frequency is quite different. If I add that together, it looks something like this, okay? If I were to show you that first, okay, you may not have seen the pattern right away, but there's a pattern, okay? But this is two components. So if you have many more together, it creates, okay, something that appears to be chaotic, okay? And it looks like something that is random, okay? So in a way, what we try to recreate and what we observe in real life is a combination of many of these vibrations. What are the vibrations coming from? So they can come from just the wheel or off-balance wheel on a trailer. They can come on characteristic of the pavement, okay? The structure of the trailer, okay? Any type of engines, okay? All of these things will be vibration that will be coming through your system, okay? And influencing what you're going to get. The suspension as well, obviously. So, to break down a complex system, okay, decompose it, okay, what is typically done, okay, is we change from the time domain to a frequency domain, okay? And to do this, okay, what it's typically done is what's called Fourier analysis. We're not going to go in great details with this, okay? I'm sure you're going to have, or you had fun with Fourier analysis in a lot of other classes, okay? And you're on top of all of this. But I'm being ironic. So you know a Fourier series, right? Okay, you can represent any types of function by basically a summation, sometimes by definition like an infinite summation of different sine or cosine function with different frequency and amplitude and so on. So what we can do is the opposite, okay? Instead of taking those components and creating a new function, we take a complex function and decompose it into simple components. So what it will take a signal like this and break it down here into two basic sine waves, okay? And if you look at the dimension of the frequency, you see a different representation of that vibration. So why is that important, and why natural force frequency are important to look at? This is the simplest example you can get, and just to illustrate the point, okay, is that what it's showing here is that if your system, let's say, it's vibrating with only a 4 hertz or 15 hertz frequency independently, you might have two components that will get into resonance, okay, at different time, and nothing's going to be damaged. Okay, but if you were to impose the system to a combination of those two frequencies, what you may get, okay, is damage. Okay, so the combination of many frequencies, okay, sometimes will result in damage that you may not see if you just vibrate at a single frequency. So that's why it's good to look at natural frequency, what they are for your package, stacks, for your product. But in the end, what really is important is you look at how your product or package or palette is going to behave when you expose it to a combination of all of these through random vibration. So what we just discussed here is Fourier analysis. Okay, what was demonstrated is complex waveform may be generated by adding sine waves with the right frequency and amplitude. That's general. So what we do here, I'm going to go through this relatively quickly, is really break down those complex signals into simple components. How do you do that? Okay, you use what's called a bandpass filter. Okay, that's basically going to look at some very narrow frequency. Usually we go 1 hertz, okay, and you go through the whole signal, okay, and break it down into its component. So you have a complex signal, and you use a bandpass filter, and you go through these different frequencies, and you can find something at 5 hertz is going to be looking like this. At 10 hertz, it might be different. Obviously, it's going to be a higher frequency, different amplitude, and so on. You break it down into many, many, many different vibrations, and you put them all together. Once you do that, okay, you get what's called the power spectral density, sometimes power spectral density, or spectral power density. Sometimes you have all these different variations. Yes?
So that machine is doing the Fourier analysis for you?
Yeah. In a way, that's what it does. So one thing that happens as an inherent property of the Fourier analysis, okay, is that the series of sine or simple sine waves coming out, like this, all have a constant amplitude, okay? So that means you're going to have something that does not vary. That means the maximum acceleration or maximum amplitude is going to be constant all the time. So this is an important shortcoming that is mentioned here, because for random vibration, the deal is that for a certain vibration, these peaks can go up and down, they can vary, okay? It depends on the system, okay? So that means you need to include a statistical approach. So instead of having, just for the Fourier analysis, let's say you have this vibration in blue, okay? What it's saying is that it's nice that we're able to identify that frequency, but in real life, that simple sine wave should have a variation in the amplitude. Does it make sense? It should be statistically distributed. So the simplest way, again, to try to look at these things, okay, and project, bless you, a model that's going to be able to generate something in the lab that will make sense, okay, is to not expect, but to assume a normal distribution of that variation in amplitude for acceleration and amplitude. So that's what's called, again, the power spectral density. And what it does, it looks at the distribution of the root mean square acceleration for a bunch of these different frequencies. And basically put it on the chart. So in here, in that equation, the bandwidth is typically usually 1 hertz. So this kind of goes away right away. So the power spectral density, okay, looks like something like this. I guess you guys were not very curious on Monday, but if you were to look at the screen I was working on in the lab, this is what you will typically see, okay? You will see a graph that will look something like this, okay, with different profile depending if you are going to be working with truck vibration, radio vibration or air vibration. Okay? So, and what this does here, what the y-axis tells you is that for a certain frequency, it's a link, if you want, to the energy associated with that vibration. So the higher is the value of the power density here, the higher is going to be the energy, okay? And typically these will be the dominant frequency that you will see into the vibration. So in here you see, we identify that these vibration, peak and vibration for road transportation around 15-20 hertz due to the tire, higher frequency here due to the structure, vibration of the floor, and the suspension is as low amplitudes, 3 to 4 hertz. So, what we're going to see is that in terms of statistic, okay, the power density, okay, is very close. So it's related to the variance about a mean value of 0g, okay? So what it is assumed, okay, is that if you look at any of these variations, okay, the average is going to be 0, okay? For a long period of time, you're going to get a 0 average. So if you take that into account, okay, and you look at the mean square, the root mean square value with a 0 average, that means that this corresponds to the variance. Okay, I'm going to write a few things on the board to illustrate this in a few minutes. And if we look at this based on the normal distribution, what you will see is that the square root of the variance is what? You guys taking statistics, right? Standard deviation. So for a normal distribution, if you look at the interval with plus or minus 1 standard distribution, it includes 68.3% of all the observed variation. If you look at plus or minus 2 of the standard deviation, if you want the square root of the value for your power density, it includes 95.4% of all the observed variation, and so on. So that means, if you go back on those graphs here, okay, if you want to know, okay, here, let's say this is pretty big, right? This is the highest level I get in that simulation, or that power density spectrum. So if I look at 4 hertz at 0.1 g squared per hertz, okay? So g squared per hertz is acceleration squared divided by the frequency range. And the frequency range is typically 1 hertz. So that means if I were to take the square root of 0.01, that will give me 0.1, right? So that indicates the standard deviation of the maximum acceleration, okay, for that range of value. So I know then, if I take that value and I create a range of plus or minus 1 time that value, so that means that all the observed acceleration I'm going to see, okay, between plus and minus 0.1 g, okay, it's going to take into account 68.3% of all the acceleration I've expected to see in those conditions. Does it make sense? Okay, and so on. So that's the idea. So I'm just going to write a few things just so it makes a little bit more sense, and we're going to stop. Oh, shoot. I turned it off. It went a little bit quicker than I expected. Just to illustrate a few things here. So, let's see. let's say you have a variable x, okay? XRMS, we're going to call that. So what would be that value, okay, if you have many of these, okay? It would be, for example, x1 squared plus x2 squared, x3 squared, blah, 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 okay? I should write this quickly. xn squared, this over n, okay? So if you want, this is the square root of sum from I equals 1 to n of xi squared over n. Okay? If you want, this is an average. This. So the bar on top here represents an average value. So for discrete value, that's what it will look like. Okay? If you were to deal with for continuous variable, what you're going to get in this case is the following. So what is the equivalent of a summation if you're working with this continuous variable? Integral, right? Okay. So that will be an integral over a certain period t, okay, of x squared dt divided by this period itself. So that will be, sorry, I'm going to change the screen and same thing. So, I don't know if you guys remember the concept of variance, okay? But the variance, by definition, okay, typically it's sigma squared, would be 1 over n, sum of I equals 1 to n, xi minus x bar squared, okay? If you have a sample or a population, you calculate the average of the whole sample, okay? And if you, for each value, you take that value minus the average and you square it, and you basically make the average of those differences, okay? Of these square differences, you get what's called the variance, okay? You can also show, if you expand this, that what is this thing equal to is the same thing as the average of the square minus the average square. And again, in that summation, if you expand this, you'll find that this guy is a constant with respect to that summation. You can simplify it, bless you, and you will get to an expression of this one. Now, that also means that if you're dealing with an average, okay, of 0, which is what we were dealing with, okay, that means that the variance is just the average of the square. And consequently, okay, the standard deviation is equal to sigma, is equal to the square root of the variance, okay? And that means that if the average is equal to 0, the standard deviation, therefore, is the square root of this guy, which would be the root mean squared. So that's what this whole concept, okay, of how we link the distribution of the acceleration to the root mean square value. It comes from this relatively simple statistical analysis. So if you were to look at mathematically what is the definition of the root mean square, You establish this, you look at the variance, okay? And then you look at the case where you have a variation with an average of 0, and you assume, you work with this normal distribution. That means, therefore, that the standard deviation corresponds exactly at the root mean square value. And if you know those root mean square value, you know with the standard deviation, with the normal distribution, what range of value you expect, depending on if you look at plus or minus 1 standard deviation, plus or minus 2 standard deviation, and so on. So that will give you a range of acceleration or amplitude that you should be expected to observe into the simulation in the environment. So those power density spectrum that we'll see, and you guys are going to see later on again, that's what they mean, okay? If you go on the vibration table and you select those things, that's where they come from, okay? People are taking the kind of complex signal. If you attach an accelerometer to a truck, you get a very complex signal. You remove the impacts, typically, because you have a pothole and things like this. These are not vibration. So those events, when you have very high acceleration, you're typically going to be removed. Then it's going to be broken down using a Fourier analysis to main component, okay? Main simple sine vibration. And they're going to be analyzed, broken down like this, and you're going to get those power spectrum density that's going to be created. So I'm going to stop here for today. And I will